So this module will build off of the preceding one on topography, and we're going to work more on spatial modeling, so combining multiple different layers together into some sort of analysis. Now there's lots of different things we can do under the subfield of spatial analysis, or spatial modeling. And really this is a set of methods whose results change when the locations of the objects being analyzed changes. So it's deriving information from data using any distributions or patterns, and then combining those together into a way that gives us one particular thing that we're trying to understand. So a model is essentially a representation of reality. It's not always going to be perfect. It's never going to be completely perfect. So it's a simplified, manageable way to view reality and to help us understand, describe, or predict a particular thing, how something works in the real world. So if we wanted to model something like erosion, we would combine together multiple layers into it. But the field of spatial analysis is more than just combining different layers together. There's several different analytical techniques under the field of spatial analysis that I want to discuss in this module because we're going to work with them during the demonstration. Some of these we've seen before. If you remember from Module 3 when we did the interactive selections on vector data. This is a type of spatial analysis. We're using multiple layers together to sort of understand one characteristic of one layer or how they interact together. So this would be a relatively simple form of this, but it's a type of analysis that we can do. So this is where we would say select all of the cities that fall within 10 kilometers of a lake or a river. We can do all of those sorts of analysis on the fly in the program itself. But what I want to extend on this is something called a spatial join. And just like we did joins with tables, where we joined two tables together, we can also do this based on spatial location. And essentially a spatial join is a way of making a permanent relationship between these two different layers. So we're going to take the information from one layer and put it into the attribute table for the other layer based on some sort of spatial relationship between them. So we can calculate this based on pretty much anything that we could do the selections on. So within, nearby, intersects, all of those different things. We can do the same sorts of calculations and create the spatial join out of them. So let's just do a quick example of this. This is the same data that we worked with in Module 3. We have rivers, lakes, states, and cities of the US and Canada, and Mexico and Canada. And we want to find the closest river to every city and how far away it is from that city. So we have our city shapefile where we have the names, and we have our river shapefile where we have the names of the rivers. So if we run this spatial join command the same way we would a regular join, what we'll end up with is a new shapefile with the nearest river and the distance to that river in the shapefile for our cities. So for every city, we know what river is closest and how far away it is. Now another type of analysis that we can do, which is somewhere between a vector analysis and a raster analysis, is something called zonal statistics. Now zonal statistics essentially summarize the variation in a raster based on the areas that we give it from either a vector model or a classified raster. So these are more commonly done with polygon shapefiles, but you could do them with some sort of classified raster if you really wanted to. Now the output is either going to be a new raster image that just summarizes that value across the entire area, or it's going to be a summary table for you. So what this might look like is here if we have all of this, the USGS quadrangles, so sort of regions of northern Indiana here, with a topographic layer underneath them. So what we're seeing is a transparent polygon shapefile with topography underneath it. What we might want to do is find out what's the average elevation for each one of these quadrangles. We can do that with zonal statistics, where we're bringing in the zonal data, we're bringing in the field that we want to use, which is just elevation, we're bringing in the raster that we want to summarize, and we're bringing in the field from the original shapefile that we want to use as the names. And what we'll end up with is a raster that looks like this, where the only value for that raster is the individual, the mean across that entire area. Now, the raster itself, I don't think is particularly useful. There's a lot of repeated data in there. It's something that would probably be better summarized by a table unless you were going to use it in a further analysis. So you can do it from a table as well. And we'll run both of these commands during the demonstration for this module. But when it generates the summary table, it gives you all of the different values. So it's going to give you the mean, the max, the number of pixels that were in that zone, the area, all of these different things. So it gives you a much more robust data set that you can then use to create a summary report of the variation across these different polygons. Now to turn to talk a little bit about more directly raster-based analysis, one that's really commonly done are distance analysis. So if we wanted to say find out how far away we are at any given spot from one location, say Notre Dame campus or something like that, we can do a couple of different ways of understanding the distance there. One of these is what we call a Euclidean distance. This is essentially a straight line as the crow flies. It's the sort of colloquial way we refer to this. And it's basically the straight line distance between 2 points on a plane calculated using the Pythagorean theorem. So it's relatively simple math. It's something we're used to thinking about. But it creates a new raster image where the only value for each cell is the distance from whatever it is we were trying to measure. So here, if we had we have 5 cities in the US named Columbia, and we wanted to find out how far away in the US we are from any city named Columbia, we can do that. We can create a raster with the distance from all of those features is the only pixel value. We're not limited to doing this to points. We can do it from lines as well. So if we wanted to find out how far away, for any place in the entire US, how far away we are from the Mississippi River, we could do that also. And you can see that the values sort of, the places where the values change sort of mirror the geography of the river as well. But we're not even limited to this. We can do it for polygons also. So in this case, if we wanted to find out how far away we are from Missouri at any point in the US, we can do that. Anything that's within Missouri is going to be a 0. Anything that's further out is going to be increasing distance from wherever the closest vertex on the edge of that polygon is. Now, in the real world, Euclidean distance is not often as important as how hard it is to get between 2 places. It's very rare that we're going to be able to follow a perfectly straight line distance between 2 points. Topography is going to be bad. There might be hills. There might be buildings in the way. There might be all sorts of things. There might be shrubs that make us want to go around certain things. So we might want to use another layer to kind of weight how easy it is to travel across a particular surface. And this is something we call cost-weighted distance analysis, where the cost raster is another raster data set that just indicates how hard it is to travel across that surface. So we can use this to create a cumulative cost of traveling from one cell to another from across that raster to a particular destination. Now, as an example of this, let's return to looking like we did in the preceding module at Crater Lake a little bit. As an example, if you wanted to go from the north edge of Crater Lake to the south edge, the Euclidean distance would be straight across there. That is completely impossible to travel. You're going to have to actually go down off the mountain, around, and come back up is going to be the easiest way. And this is based on the slope. This is based on perhaps some aspect of the fact we can't walk on water, other aspects in there. So we need to be able to have some way of weighting this so that we can understand how easy it is to travel across the surface. So let's look at an example here. So say we wanted to walk between the University of Notre Dame's library and a park that's just a little bit outside of campus here. So we have a map sort of showing these. It would look like the straight line distance, if we calculated Euclidean distance, would be relatively short and pretty easy to pass. But if we look at the topography of that area, we see that there's a hill in the way. And it may be that it's easier to walk around that hill than to try to traverse that difficult terrain. So we could weight it just simply based on the slope. If the slope is high, it's going to be harder to pass. If the slope is low, it's going to be easy to pass. If it's flat, it's going to be very easy to pass. So this is a simple way of weighting cost into these distance measurements, and something that we're going to work on in the demonstration. So this would be what our cost weighted distance looks like between those 2 points. And what I really want to stress here is that this is no longer distance. Or this is not distance in a meter-based sort of thing. This is ease of travel that it's showing us. So it's related to distance, but it's no longer the same thing. We can't just put meters on the values in this cost-weighted distance raster. So we can see that the ease of traffic, the ease of passage actually does take us around that hill. And if we wanted to look at what the ideal path would be based on the cost-weighted distance, this is what it would look like. So we'd actually want to follow it around those hills instead of traversing them directly. Now, the last type of analysis that I want to talk about is the most complicated, and this is what we really call spatial modeling. This is where we're combining multiple different things together to give us one measure of something in the real world that we might want to understand. So this is a process we call Raster Algebra, or more complex calculations. We're combining multiple layers together to model something. So these layers can be weighted based on their importance. They can be processed they need to be processed independently to reflect their importance to the final model. And this is a process we call reclassifying. So we're going to take something that used to maybe span from -1,000 to 1,000 and make it so that it's sort of scaled from 1 to 10. And then we'll do that for another layer that might have been 5 to 15, scale that to 1 to 10. And that way we get them into the same units so we can combine them together more effectively. So the process of reclassifying is essentially systematically assigning new values to a raster image based on the ranges of the old values that are in there. So we can use this to adjust different layers to the same scale. We could use it to rank differences, different values based on their importance to the final model. So if we had something that was just classified, we had something like soils, we might want to just simply go through and say sand is high, silt is low, so sand is 10, silt is 1, or something like that. So we have two different types of reclassifications that we work with when we're doing this. We have a ranked one, where we're sort of ranking things from, say, 1 to 5, or 1 to 10, or 1 to 100. So we decide what the ranks would be. This is where the sort of art behind it comes in, where the understanding of the field that you're trying to do your analysis in is important. And then we scale these different variables, these different types of data to the same scale, and then combine them into the model. In contrast, we can also do what's called a binary reclassification, where we're weighting a character as either possible or not possible. When we were talking before about traversing Crater Lake, I think it would be fair to classify everything that's water as not possible to travel across. So that would actually be something where we'd want to have water and not water as two distinct classes. So we would then multiply those variables together or add them together in a way that's going to give us a better understanding of that particular thing. So I think the best way to understand the spatial modeling process is to work through an example. And the example that we're going to work with is how to find good locations, possible locations for solar panels on the Notre Dame campus. So if we're going to do this, what we want to do is combine together multiple different layers into something that gives us a final layer that just says potential locations for these things. This is a very, very simple model that I'm using as an example. We're going to really only combine together three things. We want to have these things in a location where they're facing south because there's more southern exposure. There's more sun that they get if they're facing south. We want to have them in areas that are relatively steeply sloped so that there's a wider area that they can be put in a smaller sort of footprint. And we want to have them located a little bit far away from roads, both because they're not always the most aesthetically pleasing things, but also because we don't want to have any real overt interest or damage done to them by anything coming from the roads. So we're going to bring in a few different data layers, reclassify them, turn them into the submodels that we need, and then combine those submodels into the final model. And the original data that all we really need are a shapefile showing us where roads are, and the elevation from the DEM. So we can use that to calculate both the slope and the aspect. So we're going to manipulate those original two data layers into something that we combine together, combine those three manipulated things into our final model. So this is our DEM for the region, shows elevation. This is the first data layer we want to process. First, we're going to calculate a slope raster from it, which you can see here, sort of scaled from green to red. And then we're going to reclassify that into areas that are either with a slope of greater than 3 degrees or areas that are lower than 3 degrees. So a value of 1 means it's suitable, it's greater than 3 degrees slope. A value of 0 means it's less than 3 degrees of slope and it's not suitable for solar panels. So these are sort of symbolized here in green and purple. Green is good, purple is not good, 1 and 0. We can also create that aspect layer using the DEM, which we see here. And then we can reclassify this into the image that we actually need, which is aspects of sort of southern facing, so south and southwest and southeast. So we see these in purple here, or sort of pink. The pink ones are good aspects, south-facing slopes. The blue areas are less suitable. These are areas that are facing to the north, the east, or the west. So So the last layer that we want to bring in is our roads layer, so distance from roads. And this is a vector shapefile showing the roads sort of as a base layer that we want to then calculate a Euclidean distance from to be able to understand what the distance is and then reclassify that into our model. So this is Euclidean distance from any one of those roads. And then we've reclassified that so that anything that's greater than 1.5 kilometers away from a road is suitable. Anything that's less than that is not suitable. So that gets a 1 and gets a 0. So there are two different things we can do now for our final calculation. If we multiply these three layers together, we're going to get something that's either 0 or 1. If something's 1 in one layer and 0 in the other two, it's going to become a 0. If it's 1 in two layers and then 0 in the last layer, it's still going to become a 0. So it's either suitable or not. Or we can add them together and sort of have a ranked view of if it's a 3, then it's really suitable, it hits all three of the characteristics. If it's a 2, it hits 2 of them. If it's a 1, it hits none of them. So let's look at what both of these might look like. This is our final model if we just use either suitable or unsuitable. We have not a lot of areas. You can see them in blue here. There's some little spots in the north and some little spots in the south and the west. And the overwhelming area is not suitable in one of the three characteristics. If we add them together, it looks a little bit different. We have some areas that are very, very highly suitable. It's the exact same ones. Anything that has a 3 in this one also had a 1 in the preceding one. But then we have things that are in there, sort of the darker browns, all the way down to 0. Those are really unsuitable areas, are very dark brown. The lighter brown, the kind of tans, are 1s and 2s. So there are different ways we can rank the final thing, depending on what we want to be using the model for. So spatial modeling is not just combining 3 layers all the time. It could be many, many layers. It could be just one. It could be multiple different things, depending on what the question is that you want to address. We're going to follow this particular demonstration, or this particular module, with the next one where we look at a specialized version of this, and that's hydrological modeling.